Hello everyone. Today we are going to analyze this beam by consistent deformation method. In this beam there are two spans AB and BC. In both of the spans there is uniformly distributed load 24 kN per meter. It is acting for the full length of the beam. Both of the spans are 4 meter long. Now let us find the degree of static indeterminacy. In this beam, the number of unknown reactions and movements are 3. There are only 3 vertical reactions RA, RB and RC. The available equilibrium equations are 2. The degree of static indeterminacy will be 3 minus 2, so it will be 1. To make this beam statically determinate, let us release RB. We have removed RB. Now this is a simply supported beam and it is a statically determinate beam. We know that this is the formula we are using in the consistent deformation method. P is the final reaction or movement whichever we have removed. In this problem we have removed RB, so P will be RB. We can take delta on the other side, so it will come downwards, and we know that P is RB. Delta is the final displacement. We have removed the support B. In the support B, there is no settlement or sinking, so delta will be 0. So the formula becomes small. In the formula, first let us find delta L, which is the displacement due to the load. Here the displacement is the deflection in the point B, because from the point B only we have removed RB. If in the simply supported beam, uniformly distributed load is acting for the full span, the formula to find the deflection in the center is 5 WL power 4 upon 384 EI. Since the deflection occurs downwards, the formula should be applied as negative. Here W is 24 and L is 8. For delta L, we will get minus 1280 upon EI. Now let us find delta, that is the displacement due to the unit load. From the beam, we have to remove all of the loads and to apply unit load at B. Let us take a simply supported beam subjected to a concentrated load at the center. The formula to find the deflection is minus WL cube upon 48 EI. Since the deflection occurs downwards, the formula should be applied as negative. Here there is a difference. The load is acting upwards, so the deflection will be upwards. In this case, we have to apply the formula as positive. Here W is 1 and L is 8. For delta, we will get 32 upon 3 EI. In this formula, we have found both of them. Let us apply them. Negative into negative, it will become positive. We can take this term inversely and then multiply. EI and EI will be eliminated. For RB, we will get 120 kilonewton. By applying the rule sigma V is equal to 0, we can find RA and RC. Both of them will be same because in this beam the dimensions are symmetrical and loading is also symmetrical. RA, RB and RC are acting upwards, so all of them will be positive. The uniformly distributed load is acting downwards, so it will be negative and the distance is 8. For RC, we can apply RA. In this way, for RA and RC, we will get 36 kilonewton. Now from the point A, let us take a moment about B and to find the moment at B, MP. Let us assume that MP is a hugging moment. We have to follow right hand side rule. Clockwise will be positive and anti-clockwise will be negative. RA is acting in the clockwise direction so that it will be positive and the distance is 4. The UDL is acting in the anti-clockwise direction so that it will be negative. With the UDL we have to multiply the distance and then the distance by 2. About the span AB, MB is acting in the clockwise direction so that it will be positive. For MB, we will get 48 and it will be positive. That means our assumption is correct. MB is a hogging moment. For this particular beam with the particular kind of loading, we can find MB easily by using this formula. We have to take any span. W is 24 and L is 4. In this way also we can find MB. Now we are going to draw the bending moment diagram by superposition method. For that, first we have to draw the free movement diagram. We have to assume that every span has a separate simply supported beam. We know that if uniformly distributed load is acting in a simply supported beam for the full span, the maximum bending moment occurs in the center, and the formula to find the moment is WL square upon 8. W is 24 and L is 4. In this way we will get 48 and the diagram will be in the shape of parabola. Using MP, we can draw the end moment diagram. Since it is a hogging moment, it will be negative. We know that these are the simply supported ends. So in the ends, the moment will be 0. And the point B, the moment is 48. Using that, we can draw this diagram. Now we can combine both of these two diagrams so that we will get the bending moment diagram. Wherever both of them are together, we should not mark anything. We just keep the space empty. Wherever they are coming alone, we have to represent them with the signs. This is the bending moment diagram by superposition method. In the examination, we don't have to draw these two diagrams. We can directly draw this diagram. Now, using the right hand side rule, we can find the shear force values. Here you can see the shear force diagram. In these 2 points, the shear force becomes 0. In these 2 points, there will be maximum positive bending moment. In the beam, we can make sections in these 2 points and to find the distances. You can see that I have made two sections. The first section at a distance of x from A. The second section also at a distance of x from C. Since this beam is symmetrical with a symmetrical loading, these two distances will be same. So only at the first section I am going to find the value of x. Using the right hand side rule, we can find the shear force which is 0. RA is acting upwards so that it will be positive. The UDL is acting downwards so it will be negative and the distance is x. In this way for x we will get 1.5 meter. Now let us find the maximum positive bending moment. RA is acting in the clockwise direction so that it will be positive and the distance is 1.5. The UDL is acting in the anti-clockwise direction so that it will be negative. With the UDL, we have to multiply the distance and then the distance by 2. For the maximum positive bending moment, we will get 27 kilonewton meter. So in these two sections, the moment will be 27 kilonewton meter. The points A and C are the simply supported ends, so the bending moment at A and B will be 0. Now from the point A, let us find the moment at B. RA is acting in the clockwise direction so that it will be positive and the distance is 4. The uniformly distributed load is acting in the anti-clockwise direction so that it will be negative and the distance is 4. We know that with the UDL we have to multiply the distance and then the distance by 2. Finally, for the movement at B, we will get minus 48. We have already calculated that previously for the superposition method. This is the proper bending moment diagram. If we make this diagram upside down, that is called the bending moment diagram on the tension side. In these 2 points, the bending moment becomes 0. These 2 points are called the points of contraflexure. We can make sections in this beam and to find the distance. No need to make the sections on both of the sides. Because of the symmetrical nature, on both of the sides the distance will be same. So I have made only one section on the left side. We know that in this section the movement is 0. Using right hand side rule, we can find the movement. Then we can find the x as a 3 meter. Now we are going to end this session. Thank you for watching this video.